So part A is asking us for the free body diagram. So first I'll do block S. And then that's gravity, so Fg. Then S, subscript S. And then since it's on the surface, that's Fn, so I'll draw it up. And then Fg and Fn is equal in magnitude. And since it's moving to the right, the tension of the rope is pulling it to the right? So T is pulling it to the right. And then for block H, there's gravity pulling it down, right? Gravity pulling it down. So F, G, H. But there's also tension of the string. But since it's moving down or to the right, you know your T has to be less than your Fg, right? So let me redraw that. Okay. And then part B is asking us for a function for the acceleration. So, so I'll write out his Newton's second law. So since it's frictionless, the left side is only mg is equal to m total a, right? I'm looking at the whole system. Let me fix that. So just FGH is the force that's pulling it to the right. Now expand on it. So mg is equal to parentheses m plus m, the total mass, times acceleration. And then divide both sides by m plus capital M. So and then divide by m plus capital M. These two cancel out, leaving you with A is equal to lowercase mg all over lowercase m plus capital M. So that's your acceleration function. And then part C is asking for a function for the tension in terms of mg and A. So I'll just look at this part of the system, okay? So C, part C. So look at the free body diagram. Fg is larger, so I'll put that first. Fg, let me rewrite. So Newton's second law, and then Fgh minus the tension, the opposing force, is equal to ma, right? So now I'll plus T on this side, and then minus ma, then plus T minus ma. So this take care of this, and this T take care of that T, right? Leaving me with T is equal to Fgh minus ma, okay? Right, but like mg and a, so we have, so let me expand it. T is equal to mg minus ma, okay? So in terms of mg and a, and that's what we have. So that's done. And then part D is asking us that increasing the mass of capital M will have what effect on the acceleration tension, right? So looking at our acceleration function, capital M plus small m, if we were to increase m, we would have a larger denominator, right? So this would be large, and this is the same. So if we were to divide by a larger number, your acceleration would decrease, right? And then for the tension, since our acceleration decrease, this whole term would go down, so it would become smaller, right? So we would have mg minus a smaller number, which would increase our tension, right? So for the new diagram, we now have friction on the surface of the floor. So you know there's Fk. That has to be Fk pointing the opposite way of the motion, right? So part E. Derive an expression for acceleration in terms of m, lowercase m, capital M, mu k, and g. So first is moving to the right. So I'll take the line of motion to be positive. So I'll write down Newton's second law. Right. So now I'll put in Fg of h, right? Fgh. Then T is just an internal force, so those two T cancel out. Then minus the Fks is equal to m total A. Okay, so now I expanded it. So this is Fg minus mu k is equal to Fk over Fn. So Fk is equal to mu k Fn, right? Just multiply this over. So I'll rewrite Fks into mu k Fns is equal to m total is just lowercase m plus capital M, and then A. And then I'll expand Fns. So mg is equal to minus mu k. Then Fns is just the normal force. But since the block is on the floor, the normal force is Fg, right? So I'll rewrite that as capital M G, which is Fg is equal to lowercase m plus capital M A. And then divide both sides by lowercase m plus capital M. This would cancel out. So your acceleration function is lowercase mg minus mu k mg all over lowercase m plus capital M. Okay. So part F want us to find the t function in terms of lowercase m, capital M, mu k, and g. So part F. So I'll write out Newton's second laws is equal to ma. And then I'll look at this part of the system, and then you know that FGH is greater than T. So I'll write this first, because it's moving to the right. That's why FGH is greater than T. So FGH minus T is equal to MA. And then I'll expand on it. So mg minus T is equal, let me move it over. Mg minus T is equal to MA. And then now I will isolate for T. So plus T on both sides. T on both sides. And then minus MA. Then minus MA. Right. So this 2 cancel out. And this 2T cancel out. Leaving me with T is equal to mg minus ma. But we don't want it in terms of a, so I can plug this a function into this a, right? So T is equal to mg minus m, then parenthesis is mg minus mu k of capital MG all over lowercase m plus capital M, right? Then for part G, I'll write over here. So draw a line. Part G. With the presence of friction between the sliding block S and the surface and the level surface, would the tension increase, decrease, or remain unchanged? So first, we know that T is equal to MA, right? This is for this first equation is when there's no friction. Okay? Just by looking at, just when you look at this block right here, this is T, the only force pulling it to the right. So you get that equation. But when there's friction, you know, T minus the opposing force, which is friction, FKS, is equal to MA. Then I'll plus FKS on both sides. So this is gone. So T to MA plus FKS, right? So because there's friction, this T is larger than when it's only MA, right? Because you're adding in the FK. So to answer the question, your tension would increase when there's friction. For H is asking for the free body diagram of all three blocks. So first I'll do block H. So oops. So M and then H, right? So there's gravity, so Fg. And then assuming it's moving to the right, your tension has to be less than your Fg. So T. And then next is the large block S, right? Block S. So Fg is always there. Fg of S. Then since it's on the floor, your Fg has to be equal to your Fn. So I'll draw that as best as I can. S. And then there's tension pulling it to the right. right? But then there's also friction on the bottom. So friction go the opposite of the motion. And then there's also this contact force between the two, right? F M capital M on lowercase m, and then F lowercase m on capital M, right? And since it's moving to the right, you know that FKM and F lowercase m and capital M has to, if you add those together, they have to have a lower magnitude than your tension, right? So let me draw that. This is F lowercase m capital M, and then FK. FK, and then if you add those two together, it should be less than T, right? So let me write it out. Capital M is less than T, okay? And then lastly is the small dark blue lowercase m, right? So M. So there's gravity, so I'll draw that. Fg lowercase m, and then there's is on the floor, so there's opposite Fn equal magnitude. And then there's friction right here, Fk, and then lowercase m. So friction FKM. But assuming it's the system moved to the right, the contact force F capital M lowercase m has to be greater than FK lowercase m, right? So that's the three free body diagram. Okay, I want the acceleration given off the values. So I, the Newton's second law is equal to ma, and then we have this FGH, and then I'll just combine these two blocks so it's easier. Right, so FK is both of these two combined. FK capital M plus M. And then tension is internal force, so those two cancel out. So we have this equation FGH minus FK of capital M plus lowercase m is equal to M total A, right? So I'll keep expanding this. So this is just mg minus, and then you know that I'll write right here, mu k is equal to fk over fn. Move this over, fk is equal to mu k fn, okay? So I'll replace fk with mu k fn of capital M plus lowercase m equal to m total is just it's just this m, and this capital M, right? And then the two lowercase m are equal in magnitude, by the way. And then A. So now I'll expand Fn, okay? So mg minus mu k. Fn is on the floor, so it has to equal magnitude to Fg. And then so it's just m Then since we're adding both of the masses, your m is capital M plus lowercase m, and then g equal to, and then I'll combine this two, so 2 lowercase m plus capital M, A, right? Then divide both sides by 2 lowercase m plus capital M. Right, cancel. So your acceleration function is so now we can plug in the values to find acceleration. Okay, so let me rewrite it down here. M is equal to, lowercase m is 3 kilogram, capital M is 2 kilogram, and then mu k is 0.18. Right, so plug it in. Right, okay, so I'll simplify it a bit. So this is 29.4 minus then 8.82 all over 8. So your A is equal to positive 2.57 meter per second square. Okay, then part J, want the tension of the system. Okay, so for tension, to find tension, I'll look at this part of the system. So let me erase this and I'll separate it. Okay, part J. So we write Newton's second law. So this FG H is assuming it's still moving to the right. Your FGH is greater than T, so I'll write FGH first. Minus T is equal to MA, right? I'll expand on it. So mg minus T is equal to MA plus T on both sides, and minus MA, right? This 2 cancel out, this 2T cancel out, leaving you with this equation, right? And then I'll plug in the values to find T. So T is equal to 9.8 minus 3. A is 2.57, right? So your answer would be 21.68 Newton. But since we're taking the line of motion to be positive, so T is the opposing force, so it's negative 21.68 Newton. Okay. So now part K wants the contact force F, capital M, lowercase m. So I'll do it right here. So K, right. So I'll look at this small dark blue block right here. So rewrite second law. So it's moving to the right because of this contact force, right? And then there's also friction opposing it. F, K, lowercase m, right? So I'll write down F, capital M, lowercase m, minus F, K, M is equal to MA, right? And then plus FKM on both sides. Cancel out. And then we know that right? And then move this over. So Fk is equal to mu K Fn. So expand on that. That's it. And then that dark blue block is on the floor. So the normal force is equal to the force of gravity. So Fg. So Fn is equal to Fg. So I'll rewrite it. Okay. Now we have that. So I'll plug in all of the numbers. Plus 0.8. Which would give us positive 13 Newton. It's positive because the line of motion is moving to the right, and that's a force pushing the smaller block to the right, right? So there we go. Then for L, is asking for the speed of the block edge. So this one, right before it hit the ground, right? So L. So we can use common form. Vf square minus Vi square is equal to 2a delta s. Okay. So we know the system start from rest. So you can, so Vi is a 0. So this thing is a 0. So Vf squared is equal to 2a delta x. Delta x. Square root both sides. So Vf is equal to square root 2a delta x, right? And then take the line of motion to be positive. So Vf is equal to 2 parentheses 2.57 for acceleration is because that's what we found. Then 20 meter. So your Vf, your speed, so Vf is equal to 10.14 meter per second. Okay. In part M, calculate the time to cover the 20 meter. So we can do VF is equal to AT plus VI, right? The velocity function. And then, start from rest. So this is a 0. So technically, VF is equal to AT. So we found VF to be 10.14. Then A is 2.57. Then T. So divide both sides by 2.57. Cancel out. So T is equal to 10.14 over 2.57, which is equal to 3.94 seconds. Okay. Then part N. So part N want us to sketch a graph for all of the following. So first is position time graph, right? So position is x, and then time is t. Right. So your A is 2.57. So your speed, your velocity is increasing over time, right? So that means your distance is like quadrupling whatever your acceleration is. So your position time graph is a parabola, right? So starting from 0, it should increasing exponentially, right? Something like that. The next is velocity time graph, right? So time t and then velocity. So your A is constant, so your V is a positive constant. So your V has to be increasing starting from rest. Next is your speed versus time. So S for speed and then T. The speed is just the absolute velocity, but since velocity is already positive, your speed graph should look the same as your velocity, right? Starting from rest. And then your acceleration versus time. We know that your A is a constant, a positive constant. So I'll do this, positive constant. Then lastly, net force versus time. Oops. Net force. And then we know the function for net force is equal to ma, right? So it's A times the total mass. So that means the constant should be higher than your acceleration. So draw it up here. And that's it.